For decades at MIT, the primary challenge of intelligent systems was translation, mapping the messy logic of the real world into code. The traditional software engineering approach relied on humans to define explicit rules. To detect a face, a programmer had to mathematically describe the precise geometry of a nose or the specific curve of an eyebrow. But handcrafted logic fails against raw, high-dimensional data. There are simply too many variations in light, angle, and texture to program every possible rule. Deep learning addresses this by removing the human from the feature engineering process. Instead of following a set of predefined rules, the system ingests raw data and learns to identify the most relevant patterns on its own. It manages this complexity by routing information through layers of interconnected artificial neurons. Creating one of these models requires a specific sequence, architecting the network's physical structure, mathematically optimizing its weights, and applying constraints for real-world generalization. Moving past the industry terminology requires mastering the technical mechanics of this three-part engineering pipeline. The foundational math behind these networks has been available for decades, but it remained largely theoretical for years. These models are computationally hungry. They only became viable due to the recent explosion of pervasive digital data needed to train them. Data provided the material, but the physical catalyst was the graphics processing unit, or GPU. Because GPUs are designed to run thousands of parallel processing streams, they are a perfect match for the massive matrix multiplications required by neural networks. While data and hardware provide the fuel and the engine, the actual intelligence of the system is driven by the mathematical architecture. The fundamental building block of any neural network is the perceptron, a single artificial neuron. A perceptron calculates the dot product of numerical inputs against its internal weights. It adds a bias term to shift the output horizontally, providing flexibility. Finally, this sum passes through a nonlinear activation function, squashing the calculation into a single value. This nonlinear step is mandatory. If you combine only linear functions, the result remains linear, no matter how many layers you stack. Without nonlinearity, a network could only draw straight lines. It would be unable to map the curved decision boundaries that define real-world objects. It is the nonlinear activation function that ultimately gives the perceptron the raw capacity required to model high-level, real-world complexity. To build a full network, we stack these perceptrons into sequential hidden layers. In a process called forward propagation, raw inputs flow through these hidden layers to generate a final prediction. A new network starts with random weights. If asked to predict if a student will pass, it might guess 10%, even when actual data indicates 100%. To measure this error, we use a loss function. This formula quantifies exactly how far the network's prediction is from the ground truth. We choose the formula based on the task: softmax cross-entropy for probabilities and binary choices, and mean-squared error for predicting continuous numbers. The loss function provides the baseline metric. Without it, the network has no way to evaluate its performance or improve its accuracy. Optimization is the process of finding the specific configuration of weights that results in the lowest possible loss. Visualizing weight settings as a 3D map, an untrained network begins on a high-error peak. Gradient descent calculates the local slope to find up, then reverses it. Finally, the network takes a small downward step, governed by the learning rate. To compute the gradient across every weight in the network, we use an algorithm called backpropagation. Using the calculus chain rule, backpropagation starts at the output error and moves backwards through every hidden layer, calculating the exact adjustment needed for every weight. Backpropagation serves as the network's internal compass, iteratively guiding the weights down the loss landscape toward the most accurate solution. Calculating a gradient based on every single piece of data in a massive set is computationally infeasible on a per-step basis. On the other hand, calculating the gradient using only one data point is fast, but the results are too noisy to provide a clear path down the loss landscape. The engineering solution is mini-batch stochastic gradient descent. By processing a batch of roughly 32 data points at a time, the system gains a fast and relatively accurate approximation of the true gradient. This batching approach is specifically designed to leverage the parallel nature of GPUs, allowing the model to train at significantly higher speeds. Mini-batch SGD provides the practical middle ground that makes training large-scale neural networks possible. Minimizing loss is the goal, but if the network is too powerful, it may simply memorize the specific data points it was shown during training. This is overfitting. The model appears accurate in the lab, but because it has memorized the noise instead of learning the patterns, it fails when it sees data in the real world. To prevent this, we use regularization, a set of techniques that intentionally restrict the network to force it toward general solutions. The most common method is dropout. During each training step, the system randomly sets a portion of the neurons to 0. This blocks the network from relying on any single pathway, forcing it to learn redundant, robust representations of the data. By introducing these artificial constraints during training, we ensure the network remains functional, even when it encounters unfamiliar data. Because a neural network's capacity for optimization is so high, it will continue to lower its training loss as long as the hardware is running. We monitor this by comparing training loss against a separate test set. Training loss almost always continues to decay. However, there is a specific point where the test loss stops dropping and begins to rise. This indicates the model has started to overfit. Using a technique called early stopping, we halt the training at exactly this inflection point to preserve the model's ability to generalize. In deep learning, knowing when to stop the optimization is just as important as the optimization itself. The pipeline is complete. Data is processed through nonlinear perceptrons, optimized by backpropagation, and constrained by regularization and early stopping. Balancing these three requirements, architecture, optimization, and constraint, is what allows these mathematical systems to function as intelligent predictors. To see these architectures implemented in code, visit the Learn by Doing with Stephen YouTube channel. For deeper analysis of the evolving data systems that power these models, listen to the Stephen Data Talk podcast on any major platform.